in this video, we want to learn the formal definition of limits. Now, in one of our previous videos, we talked about an informal definition of limits, where we say that a unique real number L, okay, is called the limit of a function, let's say f, right? And if let's call f a function of x, all right? So this limit as x tends to c, yeah. So we could say that the unique real number L is called the limit of the function f and function of x as x approaches c, okay, where f does not need to be defined at c if the value of the function approaches gets closer, arbitrarily close to L, as our input value x gets sufficiently close to c. Okay, so that definition is informal, because when we use words such as arbitrarily close to L, sufficiently close to c, we may be forced to ask, we may be asked, or we may be forced to ask, whoever is teaching us, or if you are the one saying it, you may be asked, when you say arbitrarily close, how much? What do you mean? Right? How close? Sufficiently close. How close? Right? And to take care of those kind of questions, okay, or uncertainties, we bring in the symbol such as the epsilon right here, okay, and also the delta. Good. Now, epsilon here talks about error, right? Yeah, what the delta we can use it to mean distance, and this is how you're going to use it to construct the formal definition of limits. Okay, so this happens, so the limit of the function f as x tends to c is equal to L if for every, okay, let's say for every epsilon, right, epsilon greater than 0, there exists a delta greater than 0. Of course, that's what I have on my sheet. If for every epsilon greater than 0, there exists a delta greater than 0, such that, okay, whenever x minus c, sorry, this is supposed to be x, whenever x minus c is less than delta, we have f of x minus L, okay, is less than epsilon. Good. So from definition, this is equals to L, that is, the limit exists and it is equal to a unique real number L. By unique, we mean this limit gives us only one result. Okay, only one real number, right? Yeah, if for every epsilon greater than 0, there exists, or I can also say we can find, if for every epsilon greater than 0, we can find a delta greater than 0, such that when the distance for any x, okay, lies, when any x point is picked from the delta neighborhood of c, okay, what we have is that the value of the function at x picked from the delta neighborhood of c will lie in the epsilon neighborhood of L. So that may seem somehow, you may not really get it, right? So I'm going to give you a little graph just to try to illustrate what we are talking about here. So let's say the function f is just an arbitrary function, so I'm going to give it an arbitrary curve, that is any curve, right? Good. Now let's call this point C, and remember, f does not need to be defined at c. That is to say, the existence of the limit at a point is independent of the definition of the function at that point. Okay, so in that case, even if f is not defined at c, maybe we have a jump discontinuity like that, okay, so that place is a jump, or even if f is defined at c, there is no problem. So I'll just use that to denote it may or it may not, all right, just bear with us. Okay, so assuming that is the case, then we may have, if a function is defined, we may have f of c like that, or we may not, but we know where it will be, all right? But our concern here is in the delta and the epsilon, of course. Now, if such that whenever this is true, think about delta as a positive number. Of course, we say delta greater than 0, so it's positive. And if this is the delta distance from c, they have to be the same. So from here to here is delta, from here to here is delta. In other words, this point is going to be c minus delta, and then this point right here is going to be c plus delta. That is delta distance from c, okay? And this is on the x-axis. That means every value here is x value. So it can be 0, 1, 2, and so on and so forth, right? So for every x value in here, this is said to be true if whenever we pick any x value from here, the result gets into this part, and this is where the epsilon comes in. Epsilon, this place means f of x, f of c minus epsilon, this place here, while this one means f of c plus epsilon. Okay, so what we are saying in essence is that whenever we pick any x value here, okay, the result will not get past this epsilon distance from f of c. If that is the case, then the limit exists and it is equal to L. Yeah, this f of c is the same thing as the L, so don't forget that f of c is the same thing as L. So we can call this L plus epsilon. Yeah, that is the limit. All right. Let me change it to that. So whenever we pick a result here, the value is going to remain here. It will not get past, more like a tip, but it's not. It will not get past this epsilon distance from L. It will not get past the epsilon distance from L above and below. Okay, so that is just it. Okay, and let's let's do an example. So I'll just clean this part and then I'll do a little example on that. Maybe we should just use the identity function. Will not really spell out. We just use a very simple linear function, and then we can get on with it. Okay, here is an example. We have to show that the limit as x tends to 1 of 2x plus 7 is equal to 9. So that's just a limit of the linear function, and it is equal to 9. Right? Now you notice that by substitution for x equals to 1, what we have is 9, of course. So that's just it. But we want to show that that is true using the definition, okay, the formal definition of limits. Okay, so how are we going to do this? Well, we are going to use the definition, and we are going to start with this kind of setup, okay, for every epsilon, something like that. Okay, but this definition guarantees that for any epsilon that is given epsilon bigger than 0, we want to find a delta, that is, there exists, okay, that we can find such thing exists. This whole thing will be possible given that this limit exists. But if this thing is not possible, it means there's something wrong, right? So let's see. Okay, so what we want to do, we want to start off. Now this is how you start, right? Start off with proof, because we have to show. Okay, it's more like show me, prove to me, okay, that this is true. Proof, we say that given any epsilon greater than 0, okay, there exists a delta greater than 0. But I'd like to write it this way. We want to find, so that you know that that is what you want. You want to find a delta. That is, you want to prove that there exists a delta. So how do we know that it exists if we don't find it, right? Yeah, that is it. So you want to find a delta greater than 0 such that what? Okay, standing this way feels wrong. It's been a long time. Such that whenever, so as you can see, we are more like copying almost the same thing, but here is relative to the question, you will see. So that whenever, now notice this, after the whenever, we said x minus c is less than delta. This was the c, x was approaching c, okay? So here x is approaching 1, so we are going to say whenever x minus 1 is less than delta, okay, we have that word. That, observe again, this was f of x minus L. Well, the limit here is 9, so it's going to be the function minus 9, alright? So we have 2x plus 7, okay, minus 9. The absolute value of that is less than epsilon. So given epsilon bigger than 0, we want to find a delta greater than 0 such that whenever x minus 1, which is the value we are approaching, is less than delta, we have that this is less than epsilon. So our goal here is to find delta that makes this thing true. Whenever we find that, we are done. Okay, so how are we going to start? Well, we are going to start with this. Yeah. Okay, so let's see what we have. Well, using this thing, using the fact that this is true, we're going to say, okay, so from here we can have that. Maybe let me just bring a little statement now. We have 2x plus 7 minus 9, that is minus 2, right? So let me just put it, 2x plus 7 minus 9 is the same thing as 2x minus 2, all right? And from here, noting that 2 is common here, okay, we can factor it out. And by factoring, we're going to have that 2 times x minus 1, okay? But initially, in the build-up, we said that whenever this is true, we have that this is true, that is, this is less than delta. Whenever this is less than epsilon, x minus 1 is less than epsilon. Here we have x minus 1. Take note, x minus 1 is less than epsilon. So here I can easily say this is less than 2 times delta. The reason is, sorry, not epsilon, delta. The reason is x minus 1 is less than delta. So I see x minus 1, I know that x minus 1 is smaller than delta. So 2 times a smaller number, the result will be less than 2 times a bigger thing, right? So this is strictly less than delta. But you remember that in the build-up, that is from the definition, we had that this thing here is less than epsilon. Now, by trying to check it out, by simplifying a little bit here, this left-hand side here, we see that it is less than 2 times delta. So if we call epsilon 2 times delta, it means that this inequality will hold, right? The reason is we started from the definition, we got that this will be less than epsilon. Now in simplifying this, we are able to also say that this same thing, which is here, equals to this, okay? The extreme right hand side and the extreme left hand side, this is less than 2 times delta. So we can call epsilon 2 times delta. That will satisfy, all right? So from here we can see that delta is going to be epsilon over 2. So give us any epsilon, we will make delta to be half of that, and we are done, right? Give us any epsilon, delta will just be epsilon over 2, and this limit will be true. Take note, how did we start? We said given epsilon bigger than 0, given, that means we know it. We know epsilon, right? We want to find a delta greater than 0. We know epsilon divided by 2, that will give us the unknown, which is delta. That will make this thing true. In other words, this limit exists and it is equal to 9. I hope that is really clear, right? Okay, thanks for watching, and if you enjoyed the video, please don't forget to subscribe to my channel, share this video with your friends, and of course, I'll see you in our next video. All right.